So the general theory of what happens to a quantum mechanical system under a rotation of coordinates can be described as follows. Let us start by considering a system whose state is described by a ket, an abstract vector in some vector space, ket psi. Of course, this ket psi could be an ordinary function of coordinates, like for ordinary one-dimensional or three-dimensional systems, could be some complicated two-component object or a four-component object, or for all you care, some much more abstract quantity, but something which describes a state of a quantum system. When the coordinate system is rotated about a general axis n hat through an angle theta, the very same state is described by a new ket, the ket denoted by psi tilde. Notice that here we are saying that when we rotate our coordinate system in the physical world through an angle theta about a general axis n hat, the state doesn't change. It's the same state that we are describing, but we are describing this via a new ket psi tilde. Now there has to be an operator which does this, that is, changes the ket psi to the ket psi tilde, and we denote this operator by u n hat theta. Notice that this is exactly the same notation that we have been using all along. We have been calling the rotation operator, the operator which describes the action of rotation on wave functions, by u z theta, but that was because we were specifically talking about rotations about the z axis. Here we are talking about rotations about an arbitrary n hat axis. So psi tilde, the new ket, has to be the old ket psi acted upon by this operator u n hat theta. So once again, let us ask ourselves what will happen when the angle of rotation theta is an infinitesimal quantity, or is very, very tiny, let's say epsilon. So u n hat epsilon has to be essentially identity, which is the value which it will take when epsilon is 0, plus a first order correction term. And this first order correction term, apart from an I by h cross factor times the angle epsilon, has to be what describes the angular momentum component for this particular system in the direction of n hat. So for an infinitesimal angle of rotation, u n hat epsilon has to be identity plus I epsilon by h cross times n hat dotted with j vector, where j vector is a vector valued operator. So an operator which comes with three components, j1, j2, j3, and n hat dot j vector is just the component of this j vector operator in the direction of n hat. This again is correct only up to order epsilon. There are order epsilon square and higher order corrections to this. So j1, j2, j3 in this case are what we will call the three angular momentum operators. As we have already seen, in the specific case when our wave functions were described by single functions of x, y, z, these operators were nothing but the standard orbital angular momentum operators that we obtained by considering xpy minus ypx and so on. Now let me warn you about one thing which I have already stated but need to be very clear about here. In all of this we have been talking about passive rotations, situations where the system itself stays the same, it's just the coordinate system which is being rotated through an angle theta or epsilon, as the case may be. The coordinates are rotated once again, not the system. This is different from active rotations where the coordinate system stays the same but the physical object is rotated. It's pretty easy to see that an active rotation through an angle theta is essentially the same as a passive rotation through an angle minus theta. So in many books you might see the rotation operator u n epsilon for infinitesimal angles written as identity minus I epsilon by h cross times the angular momentum component, but in those cases they are considering active rotations. Active rotations being systems, the physical system is rotated, not the coordinate system. And the signs for active rotation are going to be opposite the signs for passive rotations. We are going to stick to passive rotations in this lecture, but if you go to other sources, you may find a difference in sign, and the reason for the difference in sign will usually be, unless somebody has made a sign error of course, this dichotomy between using active rotations as opposed to passive rotations. Now, so far we have been saying that when you do rotations of coordinates, passive rotations, through a coordinate transformation Rn hat theta, the ket that describes the quantum system changes. So psi goes over to un hat theta acting on psi. In this particular approach that we have been using so far, we consider the kets to change under the rotation of coordinates, while the operators themselves is the same. So this is the full story here. Psi goes over to un hat theta psi, whereas the operator O stays the same.